If someone wants to do that, it's fine. Any way to communicate to us. I feel like I'm scared. But then if I have to hold that to the case as well.
It's mine, so if you drop it, it's like.
I don't think that's true, but the worst would be marketing.
Buffalo, they have like a
Alright, thanks for coming. I'm Daniel. This is Gerard. You might remember Gerard from the basics yesterday. This is going to be the basics of Bayesian decision theory. And there's another way one could approach decision theory, which is to think in terms of justification. So why do we think that someone should be an expected utility maximizer? Why do we think that people's beliefs or rational agents' beliefs should be given by probabilities or utilities? That's not the approach we're going to take today. If people are curious about that, find us. We have like a handout on that. We could also give an impromptu talk about that kind of stuff. So we're not going to be doing a representation theorem talk today. We're going to instead be taking the opposite perspective, where we just start off with very simple models of decision problems, and then write down different decision theories very clearly with those models. And then we'll show that those models can be useful for writing down certain principles that might help us adjudicate between different decision theories. So instead of kind of thinking very grand scale and some axioms on rational preference, we're just going to assume that we have probability and utility in the background, and then we're going to think, given that, are there different ways we can formalize making decisions? Okay. I'll say feel free to interrupt me with questions along the way. However, I will also feel very free to just push them to the end if I think that it'll get us 2 minutes. So I think we do have some nice stuff we want to cover today. Okay. So I'll do the first third or so, Gerard will do the middle amount, and then I'll finish up stuff at the end. Okay. So informally, a decision problem is specified by a set of acts, so things you can do. It's specified by some probability, so some beliefs about the world and how the world is. And specified by your values, often called the utility function or value function, and that says how much you care about different things or different outcomes. And then informally, a decision theory says given a decision problem, it specifies some subset of those acts as the ones that are rationally permissible. Now the exact details of what the acts are, so like what the type signature of the acts are, or what the domain of the probability function, the utility function are, depends on the framework. First, we'll go through one framework that is a kind of toy version of the standard framework in economics called Savage. Then we'll show that Savage has certain limitations, and we'll move to a more general framework, or a toy version of a more general framework called the Jeffrey framework or the Jeffrey-Volcker framework. And then in the Jeffrey-Volcker framework, we'll be able to state things like evidential decision theory clearly, things like causal decision theory clearly, with some modifications. And then we'll look at some principles that relate to learning and decision making that we can state clearly in this framework. And then in the end, we'll gesture at how you might try to incorporate other kinds of decision theories into this framework, like functional decision theory or some kinds of updated decision theory. Okay. So we'll start off with the kind of perspective of Savage. So this is kind of standard decision framework for economics, like I said. And in Savage, you have a decision problem, which is given by this object. So it's an ordered list. You have S, that's a set of states. These are all the different ways that the world might be, where the world, in this case, is everything that doesn't depend on you. Okay. So maybe we're flipping a coin 100 times, and our decision depends on how the coin comes up. So this would be, the set of states in that case would be all the outcomes of those coin tosses. Then we have a set of consequences. So this is the kind of stuff you value, right? This is the kind of stuff you have beliefs about. This is the kind of stuff you value in Savage. So these could be like monetary payoffs is a very common example, but it doesn't have to be, right? If you're familiar with representation theorems, a lot of the idea is that this can kind of be whatever, and you're going to find some way to assign numbers to it. But these are things that tend to matter to the agent, whereas these are things that the agent has beliefs about. Then you have a set of acts. And in Savage, an act, called f, is a function from the set of states to the set of consequences. Right? So states are all the different ways the world could be. Maybe it's going to rain, maybe it's not going to rain. An act tells you, based on which state is the case, what the consequence is. So maybe an act is you bring an umbrella, and then maybe the state is whether it rains or not, so states. Consequences could be whether you get wet or stay dry.
Could those be distributions?
Could these be distributions?
Yeah.
You could have it, but like in the basic Savage framework.
No.
No. Distribution is going to live over here. Yeah. So in general, these are just whatever the actual consequences are. Okay.
Can you close that bracket?
Oh, I'm going to be writing more stuff. Yeah.
Glad someone.
Then we have a probability function. This captures the agent's degrees of belief. Like I mentioned, in Savage and the other frameworks we'll talk about, these are all derived. But for this talk, we're just going to assume we have them and then talk about choice principles based on these objects. And here the probability is going to be a probabilities over states, or really over some kind of algebra you make out of these states. Right? And then the last thing, so we can now have the bracket closed with the correct amount of space, is some kind of utility function or value function, depending how we talk about it, and this assigns a number to each consequence. Okay? So this is a super intuitive thing, right? There's some ways the world might be. There's some things you care about. And an act tells you based on, if you were to take an act, based on which way the world would be, what consequence you would get. In this framework, expected utility maximization takes on the following form. We have the expected utility of some act, f, right? So how good is it to take some act, is equal to, I'm going to write sums. We're going to assume everything's finite or countable for this talk. I think we'll actually just assume finite for the most part. Makes it much easier to write a bunch of math on the board, but in general, this is all done with integration in the most general case. So here we'll sum up over all the states, right? And we'll take the probability of each state. Here I'm being sloppy. If this is defined over the algebra, it's probably the singleton of the state, but I'll just, for the rest of the talk, ignore that and just write it over S directly. Multiplied by the utility or the value of what would happen if you were to take that act at state S. Right? So there's a few things to note here, which is that this probability, right, doesn't change based on f. We're not conditioning it on the fact that I take this act f. This is just your prior, so your unconditional probability. All of the influence that the act has over what happens is supposed to be kind of factored through this. Right? It's the kind of consequence that this act maps this state to. And then you take this weighted average, weighted by how likely you think the different states are. So I'll pause there for a second, but this is kind of, most of economics is done broadly in this kind of way. There is one feature of this framework, I think there's actually more, but like one that we'll focus on for this talk, that makes it limited and less expressive than you might want. And that feature is that it relies on something called act state independence. So this equation really would only make sense if the acts, so f here, and the states are independent in some sense. It's ambiguous if you read Savage initially whether this should be a probabilistic independence, where that would mean that you taking a certain act doesn't provide any evidence for a certain state of affairs, they're like probabilistically independent, or causally independent. But if you break the kind of independence, so if you have act-state dependence, then you wouldn't want to use this in general. But Savage explicitly assumes in the book that you've already taken how the agent thinks about the world and kind of factored it into these two independent things, the states and the acts. Furthermore, notice that you don't actually ever have a distribution over consequences unless you assume you take a particular act, and then that induces a probability distribution over consequences. Yeah.
You're saying it's safe to ignore the fact that, like, you know, my actions don't take states and consequences. My actions, like, will, like, be intervened by like physics, right? Like, states are like, you know, like, consequences arise out of like the physics that go between my actions and the consequence of them, in a sense, right? So
That might be one interpretation. I think this math is
that
very
interpretation?
agnostic for how you
it's
think
agnostic,
of it.
right? Because you can make it like a hidden composite function in there somehow.
These functions can in general be very complicated, and in fact, Savage, in his to prove his theorem, has to assume that you include every possible function from states to consequences. So you're going to get many things that look very weird from any kind of particular view of physics.
Okay.
So you'll get an act that takes you from a state where the world explodes to one where you're having tea with your family the next day. Those are
You just have to be able to entertain it as like a hypothetical objective preference.
Interesting.
But that might really go against your theory of how the world works. And
Right.
that's kind of more, what you're bringing is a kind of more philosophical objection
Okay.
to how we're thinking about acts, that when we move to the next framework, will be accounted for.
Okay. Great.
So just also maybe think of it like the states are going to be really fine grained. They're kind of like everything else
That's
aside
not
from your act. So like the state where like I flip a quantum coin and it comes with heads is going to be different from the state of the world where I flip a quantum coin and it comes with tails. Like that's like built into the
Yeah.
whatever's in
Yeah.
the state. So yeah.
Yeah, states specify everything. So it would include like the laws of physics, for example, if you're
It's
uncertain about the
included in
laws of
state,
physics.
Right.
Yeah. The only thing that's not is this kind of function. So it's a very kind of three-part system, right? You have states, which are like a different type of object than acts, which are a different type of object and consequences. The framework we'll move to in a second, everything is the same.
Great.
How does this interact with decision making over time? Where your actions do influence?
We're only going to consider decision making at one moment in time. If you want to model across time, either you take this and you think you're making some kind of plan, and you're just sending a plan you implement, so then it will kind of collapse decision making across time to a single point. Or you can work with something like decision trees, which is a bit of a richer framework that we won't discuss in this talk. Yeah. We will discuss later learning in conjunction with decision making that makes it moves in the direction of being a bit more dynamic.
Yeah.
But we'll be more talking about conditions that relate how you make a decision now based on your expectations about the future as opposed to actually moving through a tree. But you could do that.
I could, yeah.
So, like I said, right, this framework relies essentially on having this kind of factorization of how you're thinking about the world into states and acts, where there's a kind of the right kind of independence. But we want a framework that doesn't necessitate that can handle dependencies. Because that's the framework we'll move to next. People good if I erase this now?
Daniel.
Yeah.
Can I represent and compare different decision theories, say evidential and causal decision theories, in the Savage framework?
Not straightforwardly, because when you write down the set of states for Savage, you need to write them down such that they're independent of your set of acts. But the notion of independence, whether that's probabilistic or whether it's causal, is itself what's contested between evidential decision theory and causal decision theory. One, you can apply the kind of dominance reasoning that Savage appeals to throughout his framework. And so you can't really write down the same decision problem in a straightforward way that an evidentialist and a causalist might face. Because it's kind of built into the framework. Thank you.
But what if we want to?
Well, we're going to move on to the Jeffrey Bolker style decision theory framework. Jeffrey was the philosopher, Bolker was, and is, the mathematician. He's still alive. It's very nice.
Is this Jeffrey from Fire?
This is Richard
Jeffrey conditionalization.
Like Jeffrey conditionalization. Yeah. Radical probabilism. Okay, so I'm going to try to guess for Reese how much brackets I need. We might have to amend this as we go. Okay, so now we're going to think through in Jeffrey what is a decision problem, right? We had our notion for Savage before, now we're going to build it in Jeffrey. So in Jeffrey, I'm going to call these world states, and we'll contrast that later with world vectors. And the reason also I'm calling them world states as opposed to states is that these specify every matter of fact. So any particular world state, little w, that's a member of big W, unlike in Savage, which only specified everything except for things like what you do and what the consequences, this specifies just everything, including what you do in any particular world. So it's a very rich, each individual object, each individual world state is very rich. Then, like before, you have a set of acts, whereas here, acts are propositions. So a proposition is a subset of W. So in particular, what I'm suppressing in the background is you build a Boolean algebra out of W. If W is finite, which is what we'll assume in the talk, we're just going to take the power set of W. And an act here is a particular proposition. And we think of the set of acts as always partitioning W. So if this is W, right, this might be a particular act partition, right? This might be your first act, this might be your second act you could take, and this might be your third act you could take. So this is going to be some partition of W. Yes?
Like the world in which you took action 1?
Yeah, exactly. And that's why it makes sense to think of W as specifying everything, including what act you take, because, well, where did you take act A1? Well, it's all the worlds where you took act 1. So this is already very different from Savage, right? It's like completely, everything's more or less the same kind of type signature. There's also no consequences we specify. Worlds also play the role of consequences. So we have a probability function, again defined over the algebra, or I'm just going to write it usually defined over the individual worlds. And then we have what I'll call, in this case, just to distinguish it from before, on C, we have a value function that assigns particular worlds real numbers, right? So V is a function from W to the roots. And again, if you're doing the kind of big style decision theory where you're trying to justify these things, you don't start off with them, but you derive them. In this talk, we're just gonna work with them directly. Yeah.
Does like a given world also specify like all mathematical truths? Or it
It
has to
depends
be
how you want to
consequences?
think about it, but in this case, the world is supposed to specify everything the agent can think about. So if she's thinking about mathematical possibilities and statements, you'd want there to be that each world settles whether that mathematical statement she's reasoning about is true or false. So I don't want to get too distracted by this, but these are supposed to be how I think we understand decision theory, the agent's subjective possibilities. We're not assuming anything like there is a true set of background possible worlds, that the logically possible ones that she has to consider. These are just whatever possibilities she's countenancing.
So anything you have probabilistic uncertainty about.
Yeah, that's right. Yeah. So notice this is a much kind of simpler system in the sense that we don't have these three different types. We basically have worlds, world states, that play the role of states, sets of them play the role of acts, and then they also play the role of consequences. Whereas before in Savage we had this very tripart system. Okay. So any other questions about this basic Jeffrey style setup? Yeah.
So what advantage does this bring? Having this framework?
So one advantage is that there's no assumption of independence here. We didn't have to factor how the agent's conceiving of the situation into some pristine set of states that are completely probabilistically independent of what she does. In fact, a lot of the reasoning of decision theory we'll do here will be exploiting dependence as the way for understanding how acts help you get what you want, as opposed to having dependence be the kind of enemy that you need to get rid of, and think of acts in this more functional way. So I'll write down right now evidential decision theory in this framework, so I think we'll show this kind of thing directly. So,
You have that. You have it.
Okay, so we're gonna think more generally of a decision theory. Oh, we have some fancy D in our notes.
Simple as that.
The fancy D. Oh, now it's a fancy J. Okay, if this is the set of all decision problems, where a decision problem is this, and we're assuming that W is always finite here, so we're not going to run into any weird class size issues. It will in fact be a set. It'll be a function that takes you from a decision problem to the power set of, I hate this wobbly one, acts such that there is some decision problem in D. Such that A is in the act partition of D. So this is a very complicated way of saying decision theory maps you from a decision problem, a particular one, to a subset of the available acts at that decision problem. Right, so it doesn't have to specify a unique act, it just specifies some subset of acts.
So we're actually admissible.
They're actually admissible, right? So if I have my decision problem again, which will be given by this partition, right? So A1, A2, and A3. My decision theory might say, oh, you can do A1 or A2. Right, those are equally good. Or it might say, no, you have to do A2. That's the only permissible. Okay. So decision theory is just this this function, but a lot of decision theories we reason about work in terms of specifying some kind of quantity that you then maximize. So one that you've almost certainly heard of is evidential decision theory. And the quantity that evidential decision theory maximizes we'll call big V. So big V of some act A, right? This is a set of possible worlds. Right? That's equal to the sum over all the possible worlds of the probability of that world, given that we take act A, right, given A, times the value of this world state. And this is that kind of dependence that was not our enemy anymore, but we're exploiting to define the kind of notion of influence that is at play in decision theory. Did you have a question?
Yeah, I did have a
Yeah.
question. The first thing is just notational. What was the thing that you have after the last A in the power set?
This AD?
Yeah.
Yeah, this means the act partition available at decision problem D.
Yeah,
So little d is a decision problem. So in natural language, a decision theory takes you from a decision problem to a subset of the acts available at that decision problem. And this is just a
sometimes,
careful way of stating the subset of acts available at that decision problem.
sometimes we subscript all these things sometimes with little d, just being like the probability function
Yeah.
at decision problem D or the value function at decision problem D. And sometimes we just like leave it implicit because like,
Leave it implicit.
you know, it's assumed what the decision problem is.
Yeah, so I guess a second ago, I was not clear where we were going to go because it seemed like both in this framework and in the previous framework, all the information is there for you. Oh, you have this value function? I know exactly what action to take. It should be the one that gives me the biggest number. But so now you've added this structure, which is this other function which takes in the decision problem. And what the decision problem does is take a subset of the points in the
Yeah, that's right. So you'd be right that if decision problems were just you get to choose this world state or that world state, just take the one that is bigger. But the question becomes, we're not usually choosing over the most fine-grained possible description of the world. I'm choosing over propositions like, do I apply to grad school or not? That's way more coarse-grained than a world that specifies every matter of fact. And this framework can capture that at the proposition. Right? It's the set of all the worlds where I apply to grad school, some of them I get in, some of them I don't. And the question is, how do I evaluate that object, right, that act?
So what is capital D again? Is it a four tuple of those things?
This is the set of all such four tuples.
It's a set of all such.
Yeah, this is a set of all decision problems. So you can do decision theory, like evidential decision theory or causal decision theory, specifies for each decision problem a a subset of the available acts at that decision problem.
Right, I guess I'm just confused, because the right-hand side, that depends on B, capital B. So, it's,
Yeah, but this is the domain of the function, and so we're just going to say that any subset of the acts available, but then there's this further restriction that I haven't actually written down that says that the decision has to return one that a subset of acts that are available at that
Yeah.
The domain of the function is a set of
decision problems.
Yeah.
Yeah, that's right. It's a set of all decision problems with finite W, just to make it easy to.
And by definition, a decision problem is
Is
it's just a quadruple.
Yeah.
Yeah. Yeah, it's the set of possible world states. It's a set of, it's an act partition on those, right? So that's the set of world states. Here's our act partition. It's how likely you think any individual world state is, and then it's how much you value the world states. And then a decision theory specifies a subset of the act. So, oh, you should take act one, for example.
Why does that model a problem? That's
What is it? What's it?
what is a model decision problem? It looks more like a model of the world. Or like
So this is representing my uncertainty about how the world is. Right? It's like all these possible ways the world could be. And then I get to control something, like whether I walk left or right. And that's a set of worlds. It's a set of worlds where I walk left, or it's a set of worlds where I walk right, and which one of those do I end up choosing? So before in Savage, acts were these functions, but now they're these propositions. So this is the quantity that evidential decision theory maximizes, right? So like words, I just go across each world state. I ask how likely is that world state is, given that I take act A, and then I take how good it would be to end up at that world, the value of it, and I just average it out. And then if I turn this into a decision theory, it just is the one that maximizes this quantity. It returns a set of acts that maximizes that quantity. So that's evidential decision theory written down. You can see it's like very clean, it's like everything is there on the table to look at. And it doesn't, if you think of where's the influence of the act coming in, it's really on influencing the probability you're using to take the expectation. Whereas remember before in Savage, it was kind of the opposite, right? The probability stayed unchanged because we had assumed independence, and all of the influence of the act went through the mapping to consequences. So if you're someone like me, I tend to think this is a pretty good picture. If you're someone like Gerard, or other people who have more causalist intuitions, you might want a richer picture that allows us to put causal reasoning into decision theory. So now we'll turn it over to Gerard.
Cool. All right. So, like Daniel said, so far, nice picture, but we don't have like causation in here yet. So there's lots of different ways that decision theorists have tried to model causation. We're going to present a version that's associated with Richard Bradley, the philosopher, who thinks about causation in terms of these world vectors. So we're going to first, we can erase this picture. Okay, so we're going to preserve all the structure that we had originally, the set of worlds, the set of acts, the probabilities, and values. And now we're going to think about world vectors. So a world vector. I should also say at the start, I think my handwriting is to Daniel's handwriting as my slides are to Aiden's slides. Apologies. We're going to write it with, it's a little better when you're typing. Handwriting, it's kind of probably a bad choice that we use omega for the world vectors because it looks so much like W, but I'll try to make it more curved. World vector is just a function. From this actuality symbol we have, union with the set of your available actions to the set of worlds. So we suppose that you only have like a finite number of actions, which we're assuming is a finite number of worlds and everything. So Then all the world vectors will be finite, and we can just write them like this. It'll be like some world, actual, W. Say I'm gonna say like, let's say the set of actions is, A1 through AN. We have the world associated with A1, world associated with A2, so on, all the way up through AN. And that would be an example of what a world vector looks like. Right? Now what's the interpretation of these world vectors? Well, the first entry, the W, the actuality sign, we call it actual world, that just specifies like what all the banners of a particular factor are, which world is actually the case. And all these subsequent entries in the world vector specify which world would be actual if you were to take different acts. Right? So the second entry, that specifies which world would be the case if you did action 1. So which of the A1 would be actual. And same thing, the entry corresponding to A2 tells you which world would be the case if you took act 2, and so on. So this is now bringing in causal structure to the picture. Yes?
Am I to understand the actual thing as like, so these world states are so rich that they include also the actor and their decision process, and therefore there is like a world state, which is just definitely the one that actually happens because the actor and its decision process is in there. And that's that one.
Yeah, that's the first entry. Yeah. All matters of particular factors specified.
And then one of those other ones is going to be identical to it.
That's right. So one of these actions you will have taken. So maybe at the W, maybe you took act 2, A2, right? Then we actually have a couple conditions I'll write up where we try to make sure that like, your world vectors are coherent in a sense that you can't just put like any worlds in anymore. You're right. Yeah, one of these worlds will like have to correspond to the actual world. Yes.
So does this work out like the same as like Perl intervention stuff, or like more expressive or less?
Yeah, I mean, so there are a lot of similarities between this and the whole like do calculus setup. We thought about whether to include like a story of the connection between them. The story that we have to sort of connect and kind of goes by way of imaging. So there's stories of how imaging is connected with the do calculus, and we can sort of connect this stuff with imaging. But that takes a little
Imaging
bit
is
of
another way to think about counterfactuals or causal reasoning.
Not cameras.
Not cameras.
Not cameras.
So this is we think a super clean way because it just puts everything visible there in this world vector, and then you can do normal Bayesian reasoning on these world vectors. But in a lot of decision theory, people use imaging, which is equivalent to this, a pretty rich sense. And then the do calculus is in some sense equivalent to imaging. So then you get the kind of strand, but it's kind of a lot
But it is
of
a little story you need to like
to get out
to
the
build
right.
up. Yeah.
So is it a fair statement that a world vector tells you how to collapse each action, which is a set of world, to like one of its elements, plus like another way to collapse the whole into like a
Yeah, I mean, I think that's fair if I understand that right. Well, the way I think about world vectors is they specify there's matters of like actual particular fact. Like you could think about like maybe the distribution of matter in the universe or something like. And that's like those matters of fact are captured by each of all the different worlds. But that might leave unspecified matters of counterfact. Like how would things have gone if you intervened and made one part of the universe different than it actually was? Those kinds of things are captured by the entire. They're not captured by just a single world, but they are captured by an entire world vector. Because the world vector will tell you, okay, if you had intervened then A1, what would have been the case, and so on. And one actor will be the actor who actually took, and then that'll just correspond to the actual world.
And from this view, like actions are like all possible worlds in which you took the action. You only see one of them as like actual.
Yeah, there's only one action that's actually true. Right? So the actions are all propositions. The true action is the one you actually took.
I think it's asking about the type signature of W sub action. This is a set of world states, right?
W sub action. These are worlds. These are single worlds. Members of W.
Oh, I thought that the actions corresponded to partitions of group.
They do. The actions correspond to partitions, but the world vectors just have worlds in each one. So it takes out. So right, if we say you took action A1, that's compatible with lots of different worlds being true. This specifies though which one of those worlds would actually be true if you did take
Maybe
action.
one quick just
Yes.
deconfusion. You might have, in general, you will have many world vectors with the same actual component.
Yeah.
But that allows you to be uncertain about the counterfactuals. So it might be that you have two world vectors with each have the same W actuality operator symbol, right? It's the same world state. But they disagree about what would happen if you were to A3. One of them takes you to W, the other takes you to W prime. And this allows you to express uncertainty about counterfactuals.
So we'll have a probability distribution of well.
Really, yeah, we're gonna move from having a distribution over W to having a distribution over the set of all these world vectors. And then you just do normal
In the tuple, is W a set or a single world?
single.
Single worlds.
Okay, that's weird.
Yeah.
So in the top tuple.
Oh no, in the top
Oh,
two.
no,
This
that's
this is a set of
yeah,
worlds.
yeah, yeah,
The big, yeah. It's
Yeah,
harder
yeah,
when you're writing on the board versus typing.
Yeah,
It's like,
typing.
this is a big W. These are the little W's. Yeah. Okay. Okay. So there's a couple conditions we put on world vectors, but I think I'm just gonna
Sorry,
like
is that a W or an omega?
these are W's. This is an example. This whole thing
That whole thing
is an omega.
Omega
Yeah,
has
that's
teeth.
an omega.
Omega
yeah.
has teeth, and there's only one on the board right now.
Yeah.
Oh, that's right.
Yeah. This is an example of an omega. Yeah. Okay. All right. We call that like the set of all world vectors. We use like capital omega. Represent the set of all world vectors. Okay. Now we can distinguish between like factual propositions in this context and general propositions. Factual propositions are just propositions about what the actual world is. Right, so I can sort of recover all the old just sets of worlds that just specify matters of particular fact in this framework by just lumping together all the world vectors that agree on which world is actual. Right? Okay. Good. Okay. So now, probably do want to state one, have to find one sort of connective, right? So this is relevant for stating like causal decision theory. So we can introduce this conditional connective. Box arrow E, which would say like if A were the case, then E would be the case, right? This is a counterfactual proposition or a subjunctive conditional that now we can think of as basically this is going to be true at all the world vectors where in the 8th entry you find a world consistent with E. Right? The set of all such world vectors is this conditional. So
E
yes.
is a world or
A and E I'm assuming here are factual propositions. So they're just, we can think of them as just sets of worlds. They themselves are not conditionals. They're just factual propositions.
okay, so then the world that you get at a certain point,
Mm-hmm.
when you say like it's compatible with E, it means like it's
It's in E.
element of E.
Yeah, it's an element. Yeah. Okay, good. So we need that for causal decision. Okay, so now we're sort of expanding now what decision problems are, because we're moving from just having the set of worlds to now having the set of all these world vectors. And now our probabilities are going to be defined over all these different world vectors and not just particular worlds to capture uncertainty both about matters of fact and matters of counterfact.
So I think just like one interesting thing to track is that different decision theories might require more or less structure in the agent's conceptual space, right? Evidential decision theory works just fine with sticking with matters of fact. Whereas if you want to state causal decision theory, you need to introduce this richer kind of set of the structure, which is these world vectors, not just the individual world states.
Okay, but we could restate evidential decision theory in this sort of setup. Let's say the value. So evidential decision theory, of course, can tell you to maximize this V function, and that's going to be the sum now over all the omega in big omega, all the different world vectors. We're summing up the values of those world vectors, the world that's actual.
You want to put more teeth on your small omega?
You want more teeth?
Yeah,
Like-
the top where it has teeth.
Like that?
No, that works too.
Weighted by the probability that you'd have that particular world vector given you take the action A. Okay? So it's similar to before. Again, values we're assuming here are just defined directly on world states, not full world vectors. Though you could try to like generalize this and think about you care about intrinsic matters of counterfact as well if you want to. It's just right. How likely you think that world vector would be to be true if you were to take an action, right? So an action here is still just a proposition, it's still just a set of world vectors, right?
An action is a set of world vectors.
Yes.
Yeah, the action A is the set of all world vectors whose actual component, the first entry in the world vector, is a member of A.
Because remember, a world vector specifies both all matters of fact and all matters of counterfact. So one of the matters of fact it specifies is which action did you take. So collectively, they're all the world vectors that say you took action A. That's what we're identifying with action A. Yeah.
So really we're like moving between A living as a subset of W and living as a subset of omega, but there's a perfect mapping there.
Yeah.
And we're just aligning over that detail because otherwise you have to always write down this function that takes you from subsets of W to subsets of omega. But
Although like all world vectors have like an entry for A.
so they have an entry for tells you what the actual world is, and then they also have an entry that tells you what would happen were you to A.
Right.
But that set A that Gerard wrote down is the set of all world vectors whose actual component is a member of A.
Yeah.
We're
So
not looking
it's
at
a
the
factual
actual
proposition.
Yeah.
So what's the symbol in
This
tab?
one?
Yeah.
That's the actuality. So it's saying what you value is the value of you value world vectors according to what world is actual.
Yeah.
Okay, then this competes with causal decision theory, which says you should maximize a different value function. You should maximize this u, the utility, which is the sum again over world. Well, we can write it in two different ways. We could either sum over factual propositions or over all sorts of propositions. So I'll first write it in the way that it's usually written in philosophy settings. You sum over all the particular worlds. You take the value of those worlds and you weight it by the probability of if you were to take action A, then that world would be actual. So instead of weighting, this kind of aligns well with the original way of writing evidential decision theory that we had, or the original way of writing V, right, where you're basically you're summing up the values of all the worlds, but instead of weighting them by the conditional probability of that world being actual, given that you take the act in question, you weight them by the probability of the counterfactual, that if you were to take that act, then that world would be actual. Okay. We can write it in a way that's more akin to this, the way we have.
And these different ways of writing them are just they're equivalent.
They're
just
yeah.
they give you the exact same numbers.
We can write it as utility of A equals the sum over little omega and big omega, so summing over world vectors, the probability of omega times the value of omega of A. So we're sort of weighting, we're in this way of framing it, right, we're letting all the different world vectors have some say in what the value of act A should be, but the way they evaluate act A is by looking at, okay, look at my 8th entry, what world would be actual if you took act A. Okay. That makes sense.
Yeah, pause. It's a lot going on.
There's a lot going on.
Any questions?
So you called the first one evidential decision, and
The V, yeah.
The V. So this is the function that evidential decision theory says to maximize. Maximize that function.
So how do I think of the differences between these two in real life? Like, in what kind of?
Yeah. What kind of problems would they come apart?
Yeah.
Yeah. There's the classic. Do you have something that builds on?
I guess it's a follow-up.
Yeah.
I mean, first of all, is it standard? I didn't know to use V for evidential and U for causal.
That's like it goes back to David Lewis.
I didn't know.
Yeah.
And then second, I guess like if you could, if you have the time, I'd love to see this on the Newcomb problem or something like that. Is that
So that comes with your question.
Yeah,
Where do
right.
these come apart? So the Newcomb problem would be a classic illustration where these are going to come apart, right? At least on plausible ways of modeling the Newcomb problem. So if we really want to solve Newcomb, we'd have to take your description of the Newcomb problem, and we probably don't have, but maybe we can do it after.
Yeah, you we can write it.
We could write out. So we have to basically say what is the decision model that corresponds to your description of the Newcomb case, and on like plausible ways of spelling it out, we get that one boxing is going to maximize V. It's going to have higher news value to V, higher desirability, but computing values according in the way the causalist says you should according to U, 2 boxing is going to have the higher value. So we could use Newcomb. We could use a model of Newcomb to illustrate how these can come apart.
Sorry, what's What's a nuclear problem?
Oh, that's a great question.
I think with the time,
Maybe let's talk
we
deep
can
on
like,
that.
we'll go over
Yeah.
the whiteboard with
Yeah.
you.
We'll do lots of it. Yeah. Good. Okay. So,
We should note that this connection to Savage here. I think that's like now we have that.
yeah. So in this framework now, where you're saying actions now connect with states. So you can see like an act, like if you take your states to be all these different world vectors, right? The states are telling you for each act, like what world will be actual, what outcome you get. So it's kind of a nice parallel with Savage here.
Yeah, you kind of, if you remember Savage, right, here we have in evidential we have the conditional probability multiplied by the value of the actual world. Here you have the unconditional probability multiplied by the value of this function, right, that tells you that is the world, that tells you what would happen if you took that act. If you flip the act of the A, it looks strikingly like Savage. Yeah. So kind of what causal decision theory is doing, it's rebuilding Savage, a Savage style notion of an act inside of the Jeffrey Bulker framework. Cool. Good. So that was what we had. So that was a statement of causal and evidential decision theory in this framework. Then we were going to talk about learning rules. I don't think we have time to talk about.
One more question about the causal framework. So it looks like we're valuing something that can potentially be not the actual world under causal decision theory.
On this way of looking at that sort of brings that right.
How are we to interpret that?
Yeah, I mean, so on the sort of causalist view, right, all of these worlds have something to say about how valuable an action is, right? Because in all these worlds, we suppose, right, it's at least possible that you could have taken the action. You don't actually take the action in all the worlds, but it's possible that you could. And each of them therefore has something to say about how valuable the act is, right? And from a causalist perspective, like, yeah, that's the way it should be. There's some worlds where I don't actually take an umbrella to work, but it was the right thing to take an umbrella to work. And so they'll still assign utilities to that.
Is that why I'm not rich?
That's why part of why. Yeah. Do you want to close with the
Yeah, as I said, if people are interested, obviously we don't have the time to state some of the principles that we were going to give as an example, but I think it's good to spend the time to actually go through writing that carefully. If anyone wants to talk more about any of this kind of stuff, or like the cool things you can do in this framework, just come find us. I think we're both way more than happy to talk about it. But I think what's nice about this is we saw this kind of, right, we relaxed the idea of you had independence, now you end up with the Jeffrey Bulker, then you could write down evidential decision theory, which makes a certain claim about what rational choice is. But then you have different decision theory that kind of make a claim, causal decision theory, and you need to add some structure to the model in order to make sense of causal decision theory. So you might now think, starting with this kind of minimal model, if you care about other decision theories, like a kind of functional decision theory, for example, or kind of different forms of updateless decision theories, you might think, can I write it down very precisely in the kind of minimally extended version of this model, right? Like we did need to add something to write down causal decision theory, but it ended up being like very clear what we wrote down, and we can really compare how the different theories behave on the same decision problems, which I think is really nice. So I was talking with Ben earlier, who has this paper on functional decision theory, and we were saying that, okay, for a kind of update full version of functional decision theory, it actually is mathematically the same as doing causal decision theory. It's a kind of counterfactual notion, except it's just a different interpretation of what the counterfactuals are. So you might populate your world states here differently. And then if you want to kind of compare them both in the same framework, causal decision theory and functional decision theory, updateful, functional, you might just have to enrich what a world vector is. So it might be a 2n plus 1 length vector, where you have the actual component, you have what would happen on the causal supposition that you perform act A, and then you would have what happens on the function supposition you perform act A. And then we didn't really get to talk about any of the connection to learning here. So you can specify learning rules, and so changing how valuable acts seem across time. But we think that might be a nice candidate to look at where you want to package in the update full versus update list kind of distinction. And it'd be nice to write this out very carefully in this kind of minimal style framework, because then you can compare all these decision theories directly. And I think having a little toy mathematical model is super useful for doing this kind of thing. So I think we're at time, but thanks so much for coming. And really do find us if you want to chat about any of this stuff in more detail.